welcome to the second session of this afternoon seminar. We have Eugen Hellmann speaking. Explicit examples in categorical Langlands for J2 in maybe.
Okay, thanks a lot. So let me maybe start with a small disclaimer. So I'm not sure whether this talk actually fits in the seminar series. What I'm talking about is actually something which is a little bit older, maybe 3 years old roughly or something like that. And maybe the idea of this talk rather was that it's some kind of addendum to the summer school, which happened well, more than a month ago, in order to give some examples for the talks on categorical language there. But it so happens that it just can't take now because after I arrived, the first 3 weeks I couldn't write. Now maybe the room is more packed with people that actually know quite a lot about this. So I hope it's not going to be boring, but I'm trying to in some sense give you a picture of categorical local Langlands in detail for GL2, and I hope I'll be able to say something about SR2. Well, in some sense, in the spirit of if you can't make things explicit for GL2s, then maybe you don't really understand them. So if we want to understand what categorical local Langlands is, then we should be able to write down everything for GL2, at least maybe in characteristic 0. So there certainly is an integral part of the story, but I will exclusively today work over with rational coefficients of a pure bar. And implicitly from a normalizations of local Langlands correspondences, and we fix square root of q, which is maybe not so nice, but like in order to kind of make it easier to write down things without wasting time, I will sometimes implicitly use. And Q certainly yet makes no sense. So that's what's the setup. So we have F over QP, a finite extension. P is a prime which is not L. And of course, Q is the cardinality of the resonance. Okay. And then let's be on some kind of general level, at least in the first 5 minutes. So Clark and Schulze formulated a lecture for quasi-split reductive groups over F. G over F is quasi-split reductive group, which in a second will be split, and in 2 seconds will be GL2. Let's in order to write down the conjecture, let's take this quasi-split reductive group. So they say there exists an equivalent of categories between so-called Liz sheaves, pure bar sheaves on a stack called 1B. And the compact objects in there, and the bounded derived category of quasi-coherent sheaves with quasi-compact support on the stack of L parameters that I will just call X G check. Okay, so the superscript omega in here means compact objects. And maybe there's a little bit more to come to give it more structure, but let's maybe first start with this and try to explain what the left-hand and the right-hand side are, respectively, what they're built out of. Okay, so let's maybe start with the right-hand side, which is maybe easier to explain. So, so this guy here is the bounded derived category of coherent sheaves with quasi-compact support. Well, on this guy xg check, or maybe I rather should call it xLG because it depends on the L group and not on the dual group. So that's the stack of L parameters for D. Okay, and the condition with quasi-compact support here is only there because this guy here has infinitely many connected components, and you basically all the complexes there should have homologies. It's concentrated on only finitely many connected components. Otherwise, it sometimes can't be accomplished. Yes.
Do we need this nil button support thingy?
No. So in the Fark-Scholze conjecture, there is some condition on the singular support of the sheaves, but this condition vanishes if you work with rational coefficients, if you work with a QL bar. With ZL bar, there should be some additional condition over here, but this is one of the many reasons why I restrict to QL bar coefficients. All right. And so if G is split, so and then we have a dual group over QL bar, the dual group. Okay, and then the stack of L parameters is easy to write down. I mean, it's in the quasi-split case, it's also not much more complicated to write down, but I'm trying everything to save time. Then we have that x LG is x something that I want to rename it as x G check for the dual group, which is something I want to call x tilde G check divided by G check. So it's a stack quotient of the following scheme. So x tilde G check minus some scheme. Spec R goes to rho comma n, where rho is a morphism from the veil group to G check of R, which is smooth. And that is, if you restrict it to inertia, it factors to a finite quotient. And n is some element in the Lie algebra of G check in the other point, and you ask for this usual condition that if you add, you apply to the joint action of rho of G to n, then you scale then you scale the monotomy by 2 to the norm of G. Okay, so the whole thing receives an adjoint action of the group G check, and then you can pass the stack quotient. Okay. Sometimes the way how you want to write down the moduli stack of L parameters, and which is maybe studied in depth also in this case of quasi-split groups and also with integral coefficients in the work of Datam, Kowenchuk, and Mott. And I'll maybe give some explicit versions of the results in the case of GL2 later. Okay, so this at least should explain rather explicitly what the right-hand side is. Not completely explicitly, but at least all objects are defined. Okay, and so let's move to the left-hand side, which is made way more complicated. So the left-hand side, I only want to say that this deal is 1G QL bar omega has a similar orthogonal decomposition into category with the representation bounded you have categories with finitely generated cohomology of smooth QL bar representations of a group B, where B is in this coordinate set B of G, and this GB is what's called expanded pure inner form of G. Sorry?
A levy of G.
Well, I mean, I think they are called extended pure inner forms, but they are by construction all inner forms of Levy's of G. But I think at least as far as I'm aware of, the name is still extended pure inner form of G.
What is the subscript?
What is the subscript? FG, finally generated.
Okay.
Every homology group is finally generated as a representation.
Is that also called the cosmate set? Oh.
Well, let me not make it precise, up to the fact that, well, I mean, okay. I could define it, let me just do it orally. This is, you take the completion of the maximal unmodified extension of F, which has a Frobenius, okay? And then you look at Frobenius conjugacy classes in G of Z extension. Okay, so that's what it is by definition. You can prove that it's in bijection, and that's what Fark showed. That this is in bijection with the isomorphism classes of G bundles over the Fark-Fontaine curve. Up to isomorphism. But I will make this set extremely precise and tell you what the GBs are in the case of GL2 anyway. Okay, but there was this abstract story behind this. Okay, so you have this you have this decomposition, and similar functional decomposition in particular means that these categories generate the whole thing. And because there was a question what FG means, I mean, like, it's only there in order to be compatible with the compact objects up here. Right? I mean, like, that's no reason to do this. These generate, and then there's some condition on vanishings of forms in one direction. So you have the another partially ordered set. Okay, so which way did I say it's 0? It's if you are on a stratum for B, and if you are stratum on B prime, then they are 0 unless, so if they are non-zero, then they are partially ordered, then B and B prime are ordered in one direction. And what I want to say is that then B is less or equal to B prime. Okay, it maybe also depends on your choice of the partial order, whether you put things upside down or not. It could be that in your preferred sign convention it's the other way around, but I think in my sign convention for the talk it's supposed to be this one. But that's what semi-orthogonal decomposition is. Okay, but let's see what are consequences of the Fark-Schulze conjecture, and these are the things that I want to make precise in this talk. So we see that there's this functor, fully faithful functors. Did I give them names? Let's call them R, B from the derived category generated of representations of DB. I guess I will always omit smooth and QL bar because there's nothing else anyway in this talk. to this Riemann sheaves. Okay, so one conjecture is that there exists fully faithful functors like that. If you just restrict to the subcategories, okay, and one second part. The second part maybe is that there should be some kind of nice semi-orthogonal decomposition on that category over here. Okay, so that. Oh, maybe. Compatible with the fully faithful functors in here. So basically, the tangent images of these fully faithful functors should give me the semi-orthogonal decomposition, which is kind of because you have the semi-orthogonal decomposition in here, and because the whole thing is supposed to be equivalent. Okay. So let me maybe only erase half of the board first. Because the parabolic conjecture comes still with a bit of extra structure. Okay, so you should think of what I'm writing over there as a continuation of this conjecture. So there exists an equivalence of categories, which is compatible with the so-called spectral action. So with the action of the category of perfect complexes on the stack of alpha parameters with the action on both sides. Okay, where on this side it's a natural tensor action. I can tensorize the complex of Riemann sheaves with a perfect complex. And here it's a so-called spectral action that is constructed in a rather complicated way in functor, and about which I will not be able to say anything, first of all, by lack of knowledge, and otherwise, and the second reason is that the spectral action certainly will mix all these strata up there. Okay, so it doesn't make sense to talk about the effect of the spectral action on these pieces that I actually want to describe explicitly. That doesn't make any sense. They are mixed. But there is some shadow of the spectral action, which actually kind of has some relation with this explicit things over there. Namely, this spectral action. So this action induces morphism or induces morphisms from the global sections of the structure sheet on the stack of alpha parameters, which I maybe want to call that LG. Or maybe I think it's called the Spectral Bernstein tensor in functor. And well, now that should be seen as the endomorphisms of the identity functor on this category. The identity functor is just given by tensoring with the structure sheet. Okay, and hence kind of every lower section in here gives such an endomorphism. Okay, and so these things should act on here as well, and then you can restrict to this action to each stratum, and hence what you get for each stratum mapped to that GB, which is kind of Bernstein central. Okay, and what we will see is that this functors that we can construct, that they are linear. I will, with respect to that G, which I maybe will just call that check to that GB. Okay, so this category over here is certainly that GB linear category. That one here is certainly that G check linear category, and we have a canonical morphism over here, over there, which can be seen as the shadow of the spectral action of parabolic, and our functor should be linear. Okay, and there's a further desideratum for this functor, which then, together with the spectral action, actually makes it unique if it exists, as I learned last week, actually. Namely, what I like. For fixed with the datum, B, psi, so that's the short-term Borel subgroup in G, and psi is the short-term non-degenerate character of the unipotent radical. We want the compact induction from N to G, N being the unipotent radical of B, of this, so which is a smooth representation, is mapped to the structure sheet. Okay, so in fact, its equivalence will or should depend on the project side. And just one word of warning, like both objects, this object doesn't lie in this category, and this object doesn't lie in this category, which is rather easy to see just because it doesn't have quite a compact support. So in some sense, this doesn't make sense at all. Okay, so the way you should think about this certainly is that well, either you imagine that there are larger ambient categories which contain both objects, and then you have to talk about incoherent sheaves or something like this. Or the maybe easier way out is that you take some idempotent elements in the center, which correspond to, say, some finite union of disjoint, finite union of connected components. And then you apply this idempotent in here, so that you get something which is quite a complex support. And via this map, it makes sense to apply this idempotent here. It's a property of this map that this applying this idempotent actually will give you a compact object, which is only supported on finitely many Bernstein components. Okay, and once you've done this, this requirement here doesn't make sense, and then you do it for all idempotents.
It's part of the conjecture, right?
Sorry?
It's not clear that this would be the case as part of the conjecture or part of the consequence of the conjecture then. So how this corresponding idempotent will make it a compact object.
I mean, once you have this map of centers which exists due to the construction of the spectral action.
Sure.
Once you have this map, the following statement, whether true or not, but the statement is a statement that you can phrase and check. Okay, namely applying an idempotent, like an idempotent which will correspond to finitely many connected components here. If you apply this to this Whittaker representation, that you then get something which is supported at only finitely many Bernstein blocks. That's a statement which perfectly makes sense without assuming the conjecture.
It's a statement that makes sense and has been verified.
Sorry?
It's a statement that makes sense, but has it also been verified that this is the case? Or?
For GLN, certainly. For other groups, I mean, if I'm putting myself in the abstract situation that the map I'm talking about is the one constructed by the spectral action, then maybe I would rather forward this question to other people in the room, in which cases you kind of know enough about this specific map coming from Frank Scholze in order to prove this other claim, which is a claim purely representation scheme. Okay, so but for GLN and SLN, this certainly is fine, and you can, I mean, in some sense, let's see. Oh my.
For GLN, do you check it via the Helmholtz construction? For GLN, do you check it via the Helmholtz construction, or do you necessarily?
Whether you would choose by the Helmholtz construction? Well, in some sense, yes. Only that I'm just going with zero, where the Helmholtz thing actually is. The really hard thing in Helmholtz is to work integrally. Okay, and okay. I'm just going to calculate zero. It's actually very simple. You just have to, in some sense, know enough about representation. Okay. So
the equivalent of category unique, the map unique after we choose the
datum and require this, and compatibility with the spectral action, if it exists, is actually unique. Yeah. But this is the thing I just learned last week. Okay, so let's move on and maybe try to describe the GBs and the categorical representations of GB. Maybe the GL2 case. I actually want to start with the GL1 case, but maybe let's do that. Okay, so what is B of G in this case? Not by definition, but it's in bijection via the so-called Newton map or Newton polygons to the couples lambda 1 less or equal to lambda 2 in Q squared. And you require that the sum of them is an integer, and if one of them is not an integer, lambda I is not in that, then lambda 1 and lambda 2 actually have to be the same, have to be equal. Okay, so you think of them as polygons with rational slopes and integral breakup points. Okay, polygons of length 2. Okay, so the picture one usually sees is that this would be kind of 0, 0, then you have -1, 1, -2, 2, but you also have something like this, which has slope 1/2, 1/2, which is what is it actually? 1/2, 1/2. Yeah, sorry. Okay, so these are the pictures that you usually see. And this is in bijection with isomorphism classes of rank 2 vector bundles over the part container. Okay, and how does this go? So 0, 0 would be certainly mapped to the square of the structure sheet. -1, 1, you go to O of -1 plus O of 1. Here you go to O of -2 plus O of 2. And then for 1/2, 1/2, you have this rank 2 vector bundle that's called O of 1/2. Okay, and what are the GBs?
With your convention, what is the partial order? I mean,
the partial order for me is lying above.
0, 0 is bigger than -1, 1.
This,
Sorry.
no.
Is the higher one?
Well, fortunately, it's already gone. The only time I use it uploaded.
No, but you had non-trivial morphisms from GB, like rep GB1 to rep GB2, if and only if B1 is smaller or equal than B2, yeah? So what is,
I mean,
when do you have morphisms?
the open strata should be above closed ones.
Okay.
Okay, so what I want is
Yeah,
that,
the 0, 0 is bigger than,
let's say that B is, did I write it on the other sheet? So, okay, so.
no, maybe it's not, I mean, you just go on, I mean.
It's not so hard to figure it out, but so what is GB? So if B is lambda 1, lambda 2, then you have three cases that either lambda 1 is less than lambda 2, or they are the same and they are integers, or they are the same and only half integers, but not integers. Okay, so in this case, GB is T, is always F star times F star. In this case, VB is GL2 of F. And this, in this case, VB is D star, where D is a non-strip coherent. D of F coherent. Okay, so that's relatively easy. And how does the D list decompose? So first of all, you have a direct sum decomposition, but if you take objects, the direct sum decomposition over the integers. Okay, of D list G, where I fix the determinant. The determinant is isomorphic to O of n, to above. Okay, so this decomposition here just comes from the decomposition of the connected components. Okay, and this here has the same orthogonal decomposition. Into the representation categories of the GB, where where B is lambda 1 less or equal to lambda 2, and lambda 1 plus lambda 2 is N. Okay, so that's kind of an easy decomposition. And then the slightly harder decomposition is like the same orthogonal thing is kind of just included from what we had before, and it's maybe difficult to describe. But what we can do is we can decompose this further according to Bernstein maps.
You have to take compact objects on the right-hand side.
We don't forget that. I forgot. Thank you.
The require ask when B is bigger, GB is smaller, or GB is bigger.
Let's first put the omega here. What was the question?
So for B has partial order bigger, then GB is smaller, or GB is bigger.
Okay, I should really do this, okay? So what's my convention? Okay, let's see. What I want is that the bundles which are greater or equal to B in button G should be open. And this means that we have that the B prime is larger or equal to B. And if the polygon for B prime lies above that of B. Is that right? Yes. Plus okay, so that's my partial order, and I think with this partial order, the direction of the vanishing of Homs is the one that I wrote down in the beginning. Does it answer your question? I already forgot the question.
Yeah.
Okay.
Right. Saying, right, that the way you can figure this out, right, is that you're viewing these categories as embedded by a Schritt push forwards, right?
Right, exactly, yes.
So use the adjunctions between Schritt push forwards and how, well, you should get that it reduces to the star push forward to a different star pullback strata of the Schritt push forward is zero.
Right. Like there was a geometric way like to see this. It has to be equal amount if I want to have the benefit of something in the direction that I put at the beginning. But actually, I don't want too much to talk about this this Bernstein thing. But in some sense, just give you now dive into representations. Okay. So we can decompose. On the category of GB and the direct sum over all Bernstein blocks. Okay, so that's just the decomposition into Bernstein blocks. They're indexed as usual by inertial conjugacy classes of Levy subgroups of GB and supercuspidal representations of that Levy. Okay, so let's figure out what this looks like in all the three cases of B's that we have. In two of these cases, it's rather boring. So let's say I'm the torus, so F star times F star. So obviously there's no smaller Levy, so all blocks are supercuspidal. Okay, so omega is given by T and some chi1 and chi2, where chi are character. Chi character of F star to L star. Uniquely determined by this conjugacy class up to anonymified crest. Okay. And what you get is that the representations in that block the functor goes in the other direction. They are just kind of modules over polynomial ring. T mod, what I would call T naught. So T naught. So it's just the polynomial ring in two variables. And T naught is a compact sum, the maximal compact sum. So OF star times OF star. Okay, and certainly it's kind of clear what you want to do, but you have some M like this, you just take one, two, and twist it by M, and in some sense takes a diagonal action of the torus. Oh yes. Okay, and everything, so there's nothing really fancy happening. And in the case of D star, there's also nothing fancy happening. Well, I mean, up to the fact that it's much harder to classify the supercuspidal representations, but it's certainly still true that all blocks are supercuspidal. All blocks are supercuspidal. And so hence omega, sorry, I'm wasting again another chart. It's just the class of d star comma sigma, and the sigma is unique, determined by omega up to a character like this. You take the reduced norm to F star and then some unmodified character to Q F star. Okay, so that's what by definition the unmodified characters of D star. Okay, and then again, it's easy to describe this block, that this is equivalent to representations, sorry, to modules QL bar over F star or OF star, so it's denominated in one variable. Okay, so namely, let's we have some M. Let's take sigma tensor M and you take the diagonal and view M as a D representation by just applying the reduced norm and then some of this unmodified action of F star. So it's kind of more or less of the same kind like this. Okay.
QL bar, not QL.
Oh, thanks. Okay, so let me first erase the board. Well, what I want to consult and say is that these categories have an extremely simple nature, which you can also see on the side of the stack of parameters later. Okay, so I guess it's 100% clear that there will be no error in this one. So what's the last thing? Part C is GL2 itself. The only thing where something more interesting can happen. I mean, more interesting from the point of view of the categorical structure of these Bernstein blocks. Okay, so certainly in this case, for example, the classification of the supersingular representations is certainly something very interesting. But after you've done this, kind of looking at the blocks and the categorical nature of these blocks is something, well, extremely simple. Okay, so here there are three different cases, namely the supercuspidal Bernstein blocks, the principal series blocks, and there you have to distinguish between kind of twists of the principal block and principal series blocks, which are not twists of the principal block. So let me work this out. So the first thing is omega is GL2 of F, comma sigma, where sigma is supercuspidal. Okay. The second thing is well, omega is the torus, and which is again F star times F star, and let's take the case kite and the kite. So these are twists of the principal block. The principal block would be where you put the trivial representation. Okay, so kind of if the characters are the same, just it more or less looks the same. And then you have the principal series blocks which are not the principal block. So where you have Chi1 tensor Chi2. And Chi1 and Chi2 do not differ by an unmodified character. So Chi1 divided by Chi2 is running. Okay, so these are the three cases. And case 1 is extremely simple. Case 3 is almost very simple. And case 2 is the only thing where something more interesting happens. Okay, so as I'm running out of time anyway, let me just say that part 1 looks more or less the same as in part B. Okay, so as in B, up to the fact that the reduced norm is determined. Okay, but besides this, there's really no difficulty, no difference at all between these two cases. Then let's first do part 3, because this also is not so difficult. Okay, so then you can again describe this Bernstein block as modules of a certain ring, namely QL bar. So modules over the normal elegant two variables again, which is given by T mod T naught. So again, this here. Something like this. Okay, and how can I describe this? Okay, so let's just take this module over here, so which generates this category, and let me explain you where this goes. Okay, namely, what you do is you take the normalized parabolic induction. Well, what you take the Borel or the opposite Borel, in fact, will not matter at all because these turn out to be isomorphic in the of Chi1 tensor Chi2, and I twist it by this guy. So this is the representation of T of the torus, okay, which again acts sometimes diagonally. Here it's a universal unmodified character, if you want to put it like this. And then you twist it by this choice and you reduce it. Okay. And then you can maybe compute that in fact the endomorphism ring of this is exactly this polynomial ring, and then you kind of have written out a functor, and in fact you can check that it's an equivalence of categories. Okay, so in fact the endomorphisms of the thing that I put down precisely QL bar. I mean, you certainly have a map from here to here because this acts on the thing that you induced, but then this turns out to be the full thing. And with these two pieces of information, I've written down at least a functor, and I promise you this improvements of categories. Okay. Okay, I wanted to also tell you what the restriction to the Bernstein block of this Whittaker representation is. Okay, so let's do it in here. Maybe I usually don't like this, but let me for once do it color short. So if I take the representation that is supposed to normalize my my categorical Langlands correspondence, and I restrict it to this Bernstein block, what I get is just this generator that I have over here. Okay, so that's kind of it's precisely the representation up here. Okay, and you can do the same thing in the supercapacitor case. If you restrict that one to the supercapacitor block, then what you get is precisely this, well, which is also the generator of this category, which is the universal unmodified twist of my fixed supercapacitor representation in that block. Okay, so it's kind of universal unmodified. Okay, but it's kind of extremely simple to describe these restrictions. So let's now move to the interesting block, which is part 2. Okay, so let me only do the case where chi is equal to 1, because the other ones just differ by a twist. Okay, so the representations of PL2 in this block they are in fact the trivial character. For simplicity, these are the same things as the representations generated by the Iber-Hauy fixed vectors. I being the standard Iber-Hauy, which you may know are equivalent to modules over the Hauy-Hecker. Okay. So what do I want to say here? I was hoping not too much, but I just want to tell you that this category has a generator, which is the compact induction from IG trivial, which has an action of the Iber-Hauy-Hecker algebra, basically because by definition this algebra is the endomorphism ring of that one. Okay, and then you can have just tensor modules over here, and I don't want to go into left and right modules and maybe cheat and secretly identify something while making it. But the other way to make it left and right actions accurate. Okay, so this is an equivalent of categories. That's the projected generator. And what I want to describe is the center of the category. The center, well, I mean, like in all these cases, it's easy to read off what the center, what the Bernstein center is, just because they're equivalent to modules with a commutative ring, and then the swing makes the Bernstein center. So here the center is certainly the center of the Iber-Hauy-Hecker algebra. And we have a nice way of relating this to this thing that showed up all the time before, this T mod T naught, namely this compact induction IG1. This can be rewritten as some parabolic representation from the opposite well of the compact induction from the compact forward to T of trivial. Well, actually, this I also could have written as the compact induction from T naught to T of that character, Chi1 tensor to Chi2. So they can have the same thing. Okay, so it's this one. Okay, and here I have the action of that Hecker algebra to a bar of T mod T naught. And the center, so which hence gives me an embedding of the Hecker algebra of the torus in the Iber-Hauy-Hecker algebra. So this gives HT in HI. And in fact, the so-called Bernstein isomorphism, the invariants under the Weyl group get identified with the center. And this center is the Bernstein center of this category, and double with the Weyl group. Okay. I could say because it does write down the Hellmann algebra by generated in relations. You just, in some sense, know what this category is, but still I want to tell you a little bit about which objects it is. And after I've done that, I guess I should start my talk and give example of categorical local Langlands. Sorry. Okay. So this compact induction of so I is the Iwahowi, which is I view as an element contained in GL2OF, which I call K, and the GL2F, which is named G. Okay, and then I can certainly first reduce to K and then compactly reduce to the whole group, but after reducing to K, this one decomposes. Okay, so this is. If I reduce trivial from the Iwahowi to K, it's more or less the same thing up to inflation as inducing the trivial representation from the Borel of the over the finite field, over the residue field to GL2 over the residue field. And hence this one decomposes as a direct sum of trivial and some small standard representations. And I want to call it small standard. Okay, so it decomposes like this. And these are both indecomposable projectors. And in fact, every phi ID finally generated has a kind of resolution by just copies of these two representations. Kind of resolution by copies. Let me call that pi k and pi time. That's the whole. Okay, and then what we know is that we can look at the endomorphism rings of pi1. They certainly contain, of pi k. It certainly contains the center, but it's actually equal to the center. The same is true for this other one, and the homs between them are free of rank 1. They are all Z modules, of course. They're both free Z modules of rank 1, and a generator of these Z modules can also be easily written down. One of them is the resolution of the universal unmodified twist of Steinberg, and the other one is the resolution of the universal unmodified twist of the trivial representation. Okay, so let's get it right. Unmodified tilde, which is the universal unmodified character, and the other one, you take the big standard representation and twist it by this universal okay. So this gives you the whole structure of the category, at least as far as you need it in order to make all things in categorical circle Langlands precise. And oh, and the orange part is missing. Sorry. Which part is missing? Which is critical representation. If you restrict it to this compared component, then you get this indecomposable projective corresponding to this small stein. Okay. So maybe just a few words how this looks like. And on the side of previous sheaves of stacks of parameters. Decomposing XD check into connected components. Okay, so I'll try to be brief. So if you take some rho comma n in x GL2, say of QL bar, so really some L parameter, and then you can restrict rho to inertia. And then basically four things can happen. Either is what you get is some tau zero, which is irreducible two-dimensional. That's one extreme case. Then an extreme case is that you get two times the same character, a character that extends to WF, or you could be in the situation that you have two different characters that extend to WF. Okay, or you could be in the case that you have two characters that extend only to an index 2 subgroup in WF, and the other one is then a twist of that. Okay, so chi does not extend.
This is after some simplification, or
no, that's a representation of a finite group, basically, right? I mean, like, so it's IF is not finite, but it has to factors with a finite quotient, so everything has to be semi-simple. Okay, so and these two things are the simple cuspidal cases. This is the principal series, not principal block case, and that's the case with the principal block. Okay. And yeah, let me now just try to make everything precise. Okay, I will give them.
Sorry, do we have any cases where chi does not extend to the wave group?
Yes. I mean, let's talk about it afterwards. I guess right now I would not be able to straightforward give an example. Okay, so let's. Or then A, B, C, D. And A and B are super cuspidal. So A plus B correspond to super cuspidal L parameters. Okay. And then the part, let's say, at GL2 tau being so 0 or chi1. Sorry, chi plus chi w. XGL2 is irreducible. Sorry, X toward DL2 in XGL2. We have an open plus closed where rho restricted to IF is isomorphically formed. Okay, so in either of those cases, and you can easily compute, it's really just a linear algebra calculation that is isomorphic to GL1 or GL1. Okay, so let's do B. Okay, so do the principal series of parameter with the plot and equal to the plot. And let's take all this chi1 plus chi2, which do not take a binomial pi twist. Oh, that is p6. Okay, and then again, you can write this x tor GL2, and this turns out to be again just by a linear algebra. GL1 mod GL1 mod GL1 times GL1 mod GL1. Sorry, and the action always is trivial. Okay, and then B, the X, so this kind of corresponds to the principal block. And the X tor in GL2 now becomes what I mainly just want to call X, which is X tilde mod GL2, and X tilde is not just really the space of pi n modules. Okay, X tilde consists of pair pi n in GL2 times the Lie algebra of GL2 such that pi n pi to the minus 1 is q times n. Okay. And I'm going to take 5 minutes, and I'll just finish writing down where everything goes, at least for the functor of GLN, of GL2. Yeah. I'm going to write down all the functors and all the other quarter as well, but okay. Obviously, I'm always detailed.
So the GL2 action on that X tilde is conjugation on the first one? And...
well, it's a conjugation action on both vectors. Okay. So how to write down the functor? I don't know, 0 or R1 from DB finally generated of GL2 to so this functor. Okay, so I define on each Bernstein block for each omega. And so on a lot of Bernstein blocks, it just doesn't do anything. So if omega is a supercuspidal, our principal series non-principal block. Okay, so then I just have to match these blocks with the connected components up there. Okay, only need to, but let me just briefly say, only need to match the blocks and blocks with connected components of X G check, and maybe use the description of the center of the Bernstein center here, which kind of basically was the wing the modules are living over, and just see that the same wing appears on the other side. Okay, so there's like, you can make it precise and independent of choices, but maybe not in half a minute. Okay, and what's missing is the principal block. That's it. Where ID goes to, when bounded to a category, goes to on this X from up there, okay? And we have a map of X projecting down to DL2 mod DL2, projecting down to DL2, the DLT quotient of DL2 by DL2, which is the same thing as the dual torus modulo divided group, which is also the spectrum of by the Bernstein isomorphism, the spectrum of the center of the Eberhofer-Hecke algebra, and that's supposed to be a Z-linear isomorphism. And I have this representation pi 1 and pi standard, and you already know that pi standard has to go because of this orange requirement on the Whittaker datum, has to go to the structure sheet on X, and pi 1 goes to X0. So what is X0? This has two irreducible components. There's two irreducible components. So this is the irreducible component where the monodromy is forced to be 0, which looks like GL2 mod GL2. And this is where n generically is non-zero, which you also can describe as something like I even wrote it somewhere, but no, I guess I won't find it. Here it is. It's q times the trace squared minus q plus 1 squared determinant is 0. Okay, so trace and determinant are the variables in this polynomial ring, and this condition just tells that the Frobenius eigenvalues differ by okay, so let's call this function f. Okay, and then you just have to compute that the derived anamorphism ring here matches what you get. So let's say compute that there are derived anamorphisms of pi k plus pi Steinberg is isomorphic to the Eberhofer-Hecke algebra. Okay, and the thing that you just have to compute is that the derived anamorphisms of pi k are the center. Okay, like it already sits in there. You just have to compute that there are no more. And let me just give and that. Oh, sorry, not pi k. OX plus OX not. Like the other one I told you before. Okay, and then the anamorphism of, sorry, the homomorphism from OX to OX not is free of rank 1 on the projection. Like this is certainly a canonical quotient. Okay, so 3 of rank 1. And so this is quotient map. Okay, and the last thing I want to give is that also in the other direction of OX not to OX that times F bar is 3 of rank 1. And what this function F bar, I also want to tell you that this is rather explicit. Okay, so what you do is You take OX to OX. You have the quotient OX0, and what you can do is you can multiply by this element which vanishes on the connected component X0. Okay, and this factors through the and gives you the generator. Yeah. I call the function f and it's multiplication a. Okay, so this is how explicitly kind of all the generators of one category get mapped to the generators of the other category. And I should stop here, but we could describe all the reducible implementations, we could describe all the other strata as well, we could describe the same orthogonal decomposition on that category and so on. You can make all of this extremely explicit. Okay, but